Okay, off we go. Two quick announcements. First of all, apologies for the technical glitch on Wednesday that made the recordings not work. I'm still not sure what happened. I talked to my IT support, and he says it was probably just some random glitch. So the following day, I opened my computer and turned it on and did a recording, and the audio worked fine. So I think it was just one of those things. So hopefully today's recordings are going well. We'll see in an hour or so. Fingers crossed. Oh, so the other announcement, y'all got hopefully the email from me yesterday. I set up the Gradescope site for homeworks, so everybody should have access to that Gradescope site. That's where you'll upload homework 1, the email that I sent yesterday, just as a double check, detailed exactly, which sections, how we're interpreting from the class schedule, and, like that. So anyway, make sure that you're good with that. If you have any questions about the homework, you want to talk to me ASAP after class would be a really good idea while we can still talk in person. Okay. And of course, happy Labor Day in advance. So we're off on Monday, right? So I won't be seeing y'all for 5 days until Wednesday. Okay, all right. So back into the math, and here's what we were talking about last time. We just barely started into section 1.4. In particular, we talked about this idea of the geometric order of a list. This is one way to make a geometric description of an order, right? Of a list. And remember, we talked about when you have a list, specifically 2 vectors in R2, with the idea that one of them is first, the other one being second, right? The order mattering. That list is always going to be one of these 3 things. It's either counterclockwise or clockwise or linearly dependent. And keep in mind, what we mean by counterclockwise is that first vector to second vector is a counterclockwise rotation. That's what we mean by counterclockwise. And likewise for the others. And then, of course, this being a catch-all for, any situation where neither clockwise nor counterclockwise makes any sense. And it happens to be all of those are linearly dependent. Okay. All right. Now, it's arguably an arbitrary choice, right? There are other ways, I suppose, that one could make a geometric choice about how to order things, right? You could say increasing or decreasing, depending on whether the magnitude is, if the magnitude of B is bigger than the magnitude of A, right? You might call that an increasing list, and that's also kind of vaguely geometric. The reason we're more interested in this is because it connects to more other cool math constructions, and ultimately it's just more useful, right? So it's we use it because it works nicely. And some of the properties that we saw last time, these things are mirror images of each other. That's natural and therefore interesting, right? Trading the 2 vectors into different positions always changes the order. Always? Really? Every time? Yep, every time, right? And then the whole thing is independent of rotations. So that's a pretty neat list of properties, and we're going to see much better than that in just a couple of minutes here. Before we do, I want to talk about the analogous idea for 3 vectors in R3. Previously, we were looking at 2 vectors in R2. Now we're going to think about 3 vectors in R3. The analogous idea ends up involving human hands, right? So there is such a thing as a right-handed list. So if we have a list, let's put A first, B second, C third, and let's suppose that those vectors are what I have drawn over here. We call this a right-handed list, and I have to tell you what I mean by that, because this is not something that you're probably as familiar with as like clockwise, right? Y'all have been reading analog clocks for many years, I presume. So, what does right-handed mean? There's a particular hand gesture that you have to use. This is strict and rigid, and you have to use the exact right hand gesture. Whatever vector is listed first, the A vector in this case, index finger of your hand, we're claiming this is right-handed, so I'm going to use my right hand. Index finger parallel to your palm, the way index fingers want to point. Right? It's just point with your index finger, and then you point that in the direction of that first vector A, and so you see my index finger is pointing in the direction of A. Okay. Next, middle finger. Your middle finger, and it has to bend the way middle fingers want to bend. Right? Please don't get smart alecky and bend your finger backwards like this, or like to call hand yoga. Right? That's not allowed. This is inconsistent with the intention of the definition. So you have to bend your middle finger the way it wants to bend, and with your index finger already pointing in the direction of the first vector, bend your middle finger to point in the direction of the second vector. Now I have a problem here. I don't think I can make it do that, but notice all I have to do is keep my index finger pointed in the direction of A. I can totally twist as needed, right? My index finger continues to be pointing in the direction of A. So I'm going to arrange my hand like this, and now my middle finger points in the direction of B. Is everybody with me? Okay. Last step. These first two vectors, you will notice, define a plane. A plane has two sides. In this case, there's kind of the above the plane side, and then there's kind of the below the plane side. What we call the two sides doesn't matter, don't worry about it. The point is, your thumb of your right hand is going to point, and again, don't get cute, right? No contorting your hands around. Your thumb, doing what thumbs want to do, will always point unambiguously on one side of the plane. Is that cool? Everybody with me? If the third vector, C in this case, is on the same side of the plane, then that's a right-handed list. And if it's not on the same side of the plane, then that is not a right-handed list. Okay, so for example, let's look at this. Let's look at this right here. This little arrangement, right? Again, we have A, B, C. Again, the same list: A first, B second, C third. Index in the direction of A. Let's see. Now I've got to get my middle finger to point in the direction of B. Oh, yeah, that's right. I can twist my hand, right? I'm going to twist my hand like that. Now my middle finger bending like it likes. I can point in the direction of B. Now notice my thumb is on the underside of the plane that is not the same side as C. So this right here is not a right-handed list. Is everybody cool? Everybody happy? Okay. It's not a right-handed list, but it is a left-handed list. Same rules, left hand instead of right. Thumbs on the same side as C. So it's not right-handed, but it is left-handed. So you can see right-handed and left-handed are kind of opposites of each other in the same way that clockwise and counterclockwise are kind of opposites of each other. Okay. Now again, there's various things that can go wrong. They all fall into this category of linear dependence. It could be that one of the vectors is 0. I don't know how to point my fingers in the direction of the 0. There is no direction of the 0. It could be that two of the vectors are parallel. It could be, various different. The C vector could be parallel to the plane defined by A and B. Whatever. Various different such cases. They are all exactly the cases where the list is dependent. Okay, is everybody happy? Well, it turns out that this is, we already see it's kind of like clockwise, counterclockwise. These are opposites. This is a catch-all. Linear dependence is the catch-all in both cases. But it's even better than this. Not only that, but these first two cases are mirror images. Just like clockwise and counterclockwise are mirror images, right? Right hands and left hands are always mirror images of each other. If you trade the positions of any two vectors, it'll always change the order. And you can do the little hand gesture on this, but so ABC, right hand order, BAC, left hand order. That'll always work. And again, the whole story is independent of rotation. And again, I think this is pretty believable. If I have a trio of vectors that's in right hand order, right? And if I rotate the entire picture, all of those vectors, if I rotate according to the same rotation, that is still my right hand. So it's still a right-handed list. Everybody happy? All right. So I think a great way to think about right-hand order and left-hand order, these are three-dimensional versions of clockwise, counterclockwise. I think it's a great way to think about it. Okay, I am going to throw in a fourth property. This is a little bit of a cheat because technically this follows from property number 2. But I do think it's nice to list it as a property because this is going to come up a few times. So cycling a list. And what we mean by cycling is that each vector kind of moves over by one position. Oh, this one fell off, and so we go back and we put it back around on the other side. Right? So if you cycle as indicated there, you get BCA. So this is a cycling of that original list. And cycling always preserves order. So, neat fact, now again, it follows from the previous statement about trading positions, because in fact, any cycling you can achieve by doing 2 trades. And if you think cleverly about which 2 to trade in which order, you can trade twice and turn ABC into BCA. And if you think about it, if you do 2 trades, that will change the order twice, the punchline of which it preserves the order. Everybody see how that works? It's clever. Yeah. Okay. All right. Okay. So that's that. Now we're going to move on and talk about another idea. This presumably something you've seen from linear algebra class. Determinant. I'm sure you all have seen determinant before. I expect that you know some things about determinant, probably not other things. And so I'm guessing that some of the things we're going to say about determinant in this class will be new. Maybe some of these will be familiar. We'll see. Okay, before I get into the conclusions, there's a lot of setup. All of this here is just setup. The actual statements that the theorem is stating don't come until after what we're currently looking at. So bear with me for a minute while we set everything up. This is going to be about a list, 2 vectors in R2. Okay, so see R2. There's a 3-dimensional version of this theorem coming in a moment. But list, 2 vectors in R2. From a list, you can make a matrix. And it's a very natural sort of way to do it. Whatever the first vector is, make that your first column. Whatever your second vector is, make that the second column. So you give me any list, I can make an associated matrix. Yeah? Okay. All right, now here's the thing. If you have a matrix, don't forget, whoops, wrong color. When you have a matrix, you can use this formula to make a linear transformation. Right? Presumably you've seen this a million times, right? This formula right here. Any matrix can be interpreted as a linear transformation by just multiply by that matrix. Okay. All right. And lastly, given this list, we've made a matrix, we've made a linear transformation. I'm also going to make a parallelogram. And the parallelogram I'll make in hopefully an unsurprising way, but A, the first vector, I make that one of the edges. the second vector, I make it one of the edges, and then we look at this resulting parallelogram like that. Okay, is that cool? Everybody's happy with that? Feel free to raise that hand if you've got a question. Okay. By the way, before I get into the statement of the theorem, I want to point out there's a different way to think about this parallelogram. I think is really valuable. Another way to think about it: if I were to start with the unit square, that means 0 to 1 in the x direction, 0 to 1 in the y direction, right? Unit square. If I were to take that unit square and plug in to our newly created linear transformation, we would get exactly the same parallelogram. And the reason why, not hard to see, this first vector is the first column of this matrix. What happens if I plug in, let's see here. If I plug in this first edge of the unit square, if I plug in what you might call the I vector. Do y'all remember like I, J, K? Right? I hat, J hat, K hat, whatever. Those are called standard basis vectors. Standard basis vectors, very important. You, again, probably saw a lot of that in Math218 or 221, whatever you took. I like, by the way, side note, I like to call them E1, E2, and E3. It's also a very standard notation. It generalizes much more nicely. Some real advantages. You probably won't see me writing IJK very much. The book loves IJK. I would like to leave us flexible to be able to think in more than just 3 dimensions. Not geometrically, of course, right? But to be able to do algebra in more than 3 dimensions. And so I use E1, E2, E3. Okay, so first vector is the first column. What happens when I take E1 and plug into the linear transformation? Well, that just means I'm going to multiply by the A matrix, and 1, 0 times this matrix will give me that first column, namely that first vector, which is this. This. Right? So, the first edge of the unit square goes to the first edge of our parallelogram, and likewise the second edge of our unit square goes to the second edge of our parallelogram, and then you can make a linearity argument. So it's a nice reinterpretation. This parallelogram, you could think of it as coming from the original list, or you can think of it as being the image of the unit square by our newly created transformation. Okay. All right. And we are set up. Now we're ready to actually say something. And here's the first statement. Really surprising. Very counterintuitive. Remember, we have, among other things, we have this matrix. We have this parallelogram. The first statement is that when you take the determinant of that matrix, take the absolute value, you will always get the area of that parallelogram. It's weird. This is a really surprising fact. It doesn't look like it could possibly be right. I still remember very well when I first saw this fact. And I remember thinking, this is not even plausible. How could this be? Every formula I've ever seen before this one for how to compute this area, I had to compute the length of this edge. That's a square root. There's no square roots in determinant. I would have to drop a perpendicular here, which gives me another square root, and then also I would have to use trig. Where's the trig? There's no trig in determinants. Right? It doesn't look like it should have any chance of working, but it does. So, really, really surprising fact. Is everybody with me? Does everybody see how surprising that is? Yeah. Okay. All right. By the way, you do have to say absolute value. As you all know, determinants are sometimes negative, right? But areas are not. The word area kind of like the word distance, kind of like the word volume. These are intrinsically positive things. Distance means positive. Area means positive. Volume means positive. So thus the need for the absolute values. Okay. All right. Okay, next fact. The sign of the determinant, whether it's plus or minus. Namely, the thing that you were ignoring when you took the absolute value. The leftover, the thing we haven't thought about yet. The sign of the determinant will indicate the order of the list. And so, for example, this list, keep in mind A first, B second. As I have it drawn here, that list is counterclockwise. You know what I should make? Bad color choice. Let me do this. Yeah. So whether the matrix determinant is positive or negative tells you whether the list is counterclockwise or clockwise. Pretty surprising again. I mean, hard to see that coming. Where does determinant have anything to do with the geometry of how the vectors are pointing? It does not appear at a quick glance to make any sense, but it totally works. Now, specifically, as I have it drawn here, as I just stated, and you know what? I need to get back into full screen mode. There we go. As I just stated it, positive determinant means counterclockwise. So if this determinant is positive determinant, then you get counterclockwise as it's been drawn. Now, question.
I have a question. What does it mean with whether T inverse?
Yeah, I'm going to get to that. No, it's a great question, but yeah, you're just a little ahead of me. Yeah. Okay, so what I've drawn here, I had to make a choice. I arbitrarily drew A and B like this. It doesn't have to be. Let's play around with what if it was the other way. And by the other way, I mean, what if just try to get rid of that. What if this is A and this is B? Now, keeping in mind, A is our first vector, and B is our second vector. And okay, so let me get back to full screen. Okay. If the determinant is negative, the list will be clockwise, and notice that's what that is. So this is what the picture would look like if the determinant is negative. Determinant negative, that means the list is clockwise. That means like this instead of how I had it previously. Is that cool? Okay, now let's talk about the linear transformation. Again, there's a different way to think about this negative determinant. I want to think about it now from the point of view of the linear transformation. Okay, well, I already know that the parallelogram is the image of the unit square. We talked about that. So all the points in the square go to all the points in the parallelogram. Specifically, don't forget that this edge is, I hat, otherwise known as E1. And this edge, J hat, otherwise known as E2. Green goes to green, blue goes to blue. Okay, now wait a second. What does that tell me about this linear transformation? I claim this tells me lots of stuff about this linear transformation. Something very importantly intrinsic to the linear transformation. Because check this out. That original list, E1, E2, that list is intrinsically counterclockwise. It's all, E1 to E2, that's counterclockwise. While this list over here, as I have it drawn, A to B, clockwise. Now there's various things that a linear transformation can do. A linear transformation can stretch in one direction, it can stretch in the other direction, it can stretch at an angle, it can rotate, it can do shearing, right? Stuff like that. Again, it could rotate the whole picture. All of these things that I just listed, all of them preserve the order, right? If I take any list of vectors and I stretch, the order doesn't change. If I rotate, the order doesn't change. If I shear, the order doesn't change. There's only one way that you can make the order change, and that is to flip it upside down. Or said differently, to reflect through a line. So this is the alternative phrasing. The alternative conclusion is, instead of thinking about the order of the list, just realizing that it's telling you instead, it's telling you there is a reflection hidden inside of your transformation. Or the way that I wrote it, come on screen, there we go. The way I wrote it, this transformation here inverts the plane. And I like to use this word inverts because you don't have to think of this as a reflection. This would be a reflection through a line, maybe about like so or something. Of course, you got to do more stretching and shearing and whatever. But you can think of it as a reflection, or you can think of it as a flip. Flipping it over. And take your pick. You can think of it in either one of those ways. Is that cool? This is the part that I think most students had not seen. And again, it is equivalent to just asking if the list is clockwise or counterclockwise. What's different about this is that the list is static. The function is kind of an action. And there are some situations where knowing how to interpret determinant in relation to the action, to what's happening, to a function that's doing stuff, can be really, really useful. Okay. All right. Okay. Questions before we go on? It's a big theorem. A lot of stuff to write down. Oh, there's the third case as well. That's a pretty straight read. Oh, there's so much to delete. Okay. This theorem about two vectors in R2 has an analog about three vectors in R3. And the theorems are so closely analogous, I deliberately laid them out on the page to be kind of, this is a rip-off of the previous. Look how that lays on the page. Look how this lays on the page. They are morally the same theorem. Two vectors in two dimensions make a 2x2 matrix, and a two-dimensional linear transformation that we relate to a two-dimensional notion of size, right? Area is a two-dimensional notion of size, and a two-dimensional notion of an inversion, namely a reflection through a line. This theorem, it's about three vectors in R3 making a 3x3 matrix and a three-dimensional kind of a three-dimensional analog of a parallelogram. It's called a parallelepiped. Its three-dimensional notion of size, namely volume, and the three-dimensional notion of order, namely right and left hand, not clockwise, counterclockwise, and a three-dimensional notion of a reflection, namely reflection through a plane. So it's what I'm going to call morally exactly the same theorem. I'm not going to talk through the details because it's all the exact same stuff that I just said before, just now three-dimensional instead of two. So that's pretty wild. Okay. Questions about this before we go on? Okay. Again, really surprising fact. By the way, ask yourself, if somebody came to you with a list of 3 vectors and said, hey, by the way, look at that parallelepiped, now compute that volume for me. And you're like, okay, I guess I have to chop up this parallelepiped into a bunch of, oh my gosh, that would turn into a nightmare of a geometry problem fast, right? Horrifying to think how hard that would be. Or you can just compute the determinant. You're done quick. All right, cool stuff. All right, moving along. We're going to define now, finally, we're going to finally get around to defining the cross product. I want to set the context a little bit first. I'm going to digress from what the book does pretty significantly. There's nothing wrong with the book's presentation. But I think there's some really big advantages to doing it my way. And by the way, this is not a two-sided argument. There's a bunch of different ways to talk about the relationships between cross products and determinants and handedness and this kind of thing. And everybody's got their own favorite order of how to do things. And so I've got mine, Tali's got hers, pros and cons, right? So I'm not judging. So we're going to do all the same stuff, but it's kind of from a different point of view. Kali's approach is mathematically has certain nice advantages. What Kali does is more rigorous. I think that's what we're here for, right? I think I'm more interested in intuition and sort of geometric sort of, being able to understand and see things, get familiar with how they work geometrically. I am more interested in what I'll call aha moments, right? Where you're like, oh yeah, I see that now. That kind of thing. That's what we're interested in. Right? And the fact that what I'm going to do is a little bit less rigorous, oh well. Not our problem. By the way, let me point to where my lack of rigor is. You will notice with this theorem that there is no proof included here. How do I prove this theorem? And there's 2 different ways to prove this theorem. One is brute force with trig and lots of algebra. In the book. Feel free to take a look. You're welcome to think of it that way. Rigorous. Can't argue with it. Ultimately, though, pretty unsatisfying. When there's massive algebra, I feel like there are no sort of aha moments. There's no clarity. There's no satisfaction. I'm a big believer in the following idea. You want to know not just that things are true. You want to understand why they should be true. Does that make sense? Right? If you can make the case, well, this kind of has to be true. Well, of course it's true. If you have some sense, right, some intuition for it, I think that's really the goal. I think that's what allows you to have the best sort of working proficiency with a collection of ideas. So her proof, I complain, it's not very satisfying. Fairly opaque. It's very unintuitive in that sense. There is a second proof I know of for how to prove this. It's very beautiful. It's a very aha moment. It's very satisfying. And it uses mostly linear algebra, so it's not really quite what we're here for in that sense. It's linear algebra that's a little bit beyond what y'all have seen before, not tremendously beyond, but maybe a little bit more than y'all are prepared for. And it's just not really quite an appropriate proof for us to talk about in this class. If you are curious, I would love to show you in office hours. At least I can hit the highlights. I think I can persuade you. I think I can give you the aha moments. If you come ask me in office hours, I'll be happy to. You're not required. You don't have to. Much better proof. And so my take is that when there is a much better proof, what's the purpose of the inferior proof? I think the one with lots and lots of trig and algebra is, my gosh, who needs it? There's a much better proof out there. So I don't see the point in showing you the tedious proof. Okay. All right. So punchline. The shortcoming in my presentation is I'm not going to prove one of my foundational facts. Okay. And I think the payoff is worth it. Okay, so here's a definition. We're going to define this thing called the cross product. cross product of two vectors is defined by that formula right there. You should be wondering why? Where did that come from? What an odd formula to write down, right? It doesn't look very natural. Looks pretty weird. And that's all correct. So I'm going to slowly, one step at a time, show you reasons why you should like this formula, reasons why this formula is very valuable. So here we go. First one, this formula is equivalent to this formula with determinant. And now there's a problem with this formula, but I'll confess to the problem in just a moment. Let's first talk about how great this formula is. You put the standard basis vectors along the top. You put the first vector in the next row, and you put the second vector in the last row. Nicely, sort of easily organized. You all know the formula for determinant, plug and chug, and you will produce, in fact, exactly this formula. Now, confession time. I wrote determinant. When you take a determinant, that's supposed to be a matrix. When you have a matrix, aren't these elements supposed to be numbers? Right? Was anybody weirded out by that when you first saw like, hey, wait a minute, you can't just stick anything you want in that. Like, can I just make this entry instead of the number A3? Can I put purple? That's not a number. You can't put purple where a number is supposed to be. It's got to be a number, right? So likewise, this is a vector. You're not supposed to put a vector where numbers are supposed to be. So this is a very legitimate complaint. Y'all have no experience with matrices whose elements are anything other than numbers. And I can't just go around changing the rules on things like that, right? So this is a valid complaint. That said, if I say, let's just consider what I'll call the symbolic determinant, forget about the fact that this is a very suspicious looking matrix, right? And just pretend that everything's fine. Just go across the top row, cross out the row, and look at the sub-matrix, AD minus BC. Do the usual formula, write it down, completely blind to the fact that it may be nonsense. If you just write it all down, you will get this formula. It works. And so it's kind of a nice little shortcut, little hack, little nothing else memory technique. So this is the formula that I encourage you to know. That's the only formula for cross product I've ever memorized in my entire life. I have never memorized that formula. I've computed a bazillion cross products, and I've never used that formula. And I suggest you shouldn't either. This, I don't think I could forget it if I tried. It's so easily organized. This, if I were to try to memorize this, I am 100% sure I would at some point I'd get two of them backwards, I'd mess up a minus sign, and I know I would. It's a question of time. Okay. Yes?
If you're computing determinant field, basically ignore the first row because we're not considering that. So
yeah, if you're use a different row or a different column, it still works. Yeah, absolutely. It's a little bit weirder to write it down. It's a lot more trouble, but it would give you the same answer. Yeah, so I would suggest you just go across the top row, and things work out really nicely.
I also thought that what if we just write something else instead of the standard basis? Because we'll still ignore that.
No, this formula only works if we put the standard basis vectors in there. That's a requirement to make the formula work. Yep. All right. Cool. All right. Here's a cool fact. If you take this cross product and then you take any other three-dimensional vector, and if you compute a dot product of the green vector with the blue vector, So C dot A cross B. All right, just punch out this dot product. Y'all know how to do dot products, and we have a formula here for the cross. If you just dot that, multiply it out, collect all the terms, what you will find is that this dot product is literally a determinant. And there's no asterisk on this. This is a straight up, honest to God determinant, good old fashioned Math219 determinant. These are all numbers. This is just a matrix. No asterisk. Again, deserves to be checked, right? So go, write all that down, go across the top row, compute the determinant, do the usual. It's not hard to see it happening. As you go across that top row, you'll be producing sort of one term at a time, the exact terms that you produce in that dot product. Okay. All right, so really neat fact. The reason we care about this, so this is called a triple product. This expression here is called a triple product. The reason we care about the triple product formula is because it relates something that we don't understand to some things that we do understand. Right? We do not really have a good understanding of cross product. Right? Where did this formula come from? What do we do with it? What's it good for? We don't know anything about it. But we know dot products. We're good at dot products. We know determinants. We have a lot of knowledge about determinants. This is a foot in the door. This is an opportunity to learn more about cross products. And if you follow through the notes, this is exactly what happens. This is the foot in the door that makes them all possible. Okay. All right. Okay. All right. Now here's where I have to, this is always very disappointing to me. But the proofs that will follow various theorems we're about to talk about. They take up too much time. We don't have that much time. We have so many other things to do. And again, I have to make these tough choices. I hate having to do that, right? But I have to decide how to spend class time. And this stuff doesn't make the cut. But since this is also not in the book, and it's sufficiently clever and such that I don't really feel comfortable asking you to walk through it either, y'all are not responsible for it, right? So I say not expected to be tested. So you don't have to look at these proofs, and we're not going to talk about these proofs. Now, I do say optional because I do think it's good background. It's good practice, right? If you want to get practice in how to think about cross products and how to use sort of geometric interpretations of these various tools that we're talking about and how to relate ideas to other ideas, I think this stuff's fabulous. It's great practice, right? So I encourage you to look at it. You don't have to, and I'm not going to directly test you on these proofs. Does everybody understand the take there? Okay. All right. So but to be clear though, you do have to know the theorems. The theorems are fair game. That is part of the course. So make sure to follow along with the theorems here. Here's the first one. If you have a couple of vectors A and B, and if you cross them like so to get that third vector, that cross product is always, wrong color. That cross product is always orthogonal to both of the inputs, A and B. So, said differently, give me any two vectors, the cross product will always produce a new vector that's perpendicular to both of the originals. It's a fabulous tool for creating stuff that's perpendicular to what you have. Everybody understand the statement there? Okay. Really useful tool for that purpose. Cool proof. Give it a look if you're so inclined. You don't have to, but I think there's good ideas in there. Yes, sir?
By the A cross B, you mean the resulting vector is perpendicular?
Absolutely. Yeah, that's right. So when we write that means, the thing that is produced when you do that cross product. Absolutely. Yeah. All right. Okay. Next fact. The triple product. When you cycle the vectors, when you move that one over to there and that one over there and that one fell off and you come back and put it back over to there. When you cycle through the list, the triple product doesn't change. Now this, at a quick glance, when you just kind of look at how this lays on the page, it kind of reminds us of back in I don't know how elementary school worked for y'all, but for me, they made me learn stuff like the distributive property and the associative property, and we wrote down a bunch of stuff that at a quick casual glance looked like that, and I just remember thinking, well, this stuff is all obvious. Why would you give a name to such a trivial observation? A times B equals B times A. Oh, we're going to call that the commutative property of multiplication. What a big word for such a small idea, right? So this looks like one of those, but it's not, right? This is not like an associativity or something. This is a really different thing. And from an algebraic standpoint, from a plug and chug standpoint, it is not at all clear that this is going to work out. Here I'm crossing B and C. Here I'm not. Here I'm crossing C and A. A used to be outside of the cross product. Now it's inside of the cross product. It is not at all clear that these will be the same. Mysteriously they are. And by the way, not so mysterious when you just remind yourselves, these triple products are of course all determinants. So y'all already know that determinants behave nicely when you shuffle columns. So really not that surprising at all. Okay. Here's a super weird one. I wish we had time to talk about this proof. It's a really, really beautiful proof. If you have two input vectors, A and B, if you cross those vectors, well, you get a vector that's perpendicular to both. If you then take the magnitude of that cross product, if you think about how long that vector is, amazingly, you will get the area of the parallelogram that the original two vectors describe. And by the way, I have this little notation that I made. I either made or I remembered but forgot where I remembered it from. I don't know how to decide. But this parallelogram defined by the vectors A and B, I think it's a handy, compact way to say the parallelogram defined by A and B. It's very compact. Anyway, amazing fact. The length of that vector is the area of this parallelogram. Super weird. You wouldn't expect that to be the case. But again, true. And really nice proof. And again, I encourage you to take a look. It's very, very clever. I never would have thought of this on my own. To be clear, I did not think of this proof. Somebody showed me this proof. Very clever. When the cross product is 0, the list is dependent. That's a pretty cool one. By the way, if either of the vectors is 0, I'm going to say that's obvious. So let's consider what happens when neither vector is 0. So let's talk about the non-zero case. Remember, in the non-zero case, linearly dependent means parallel. So another way to say this, ignoring 0, ignoring boring, right? 0 is boring. Ignoring that, when the cross product is 0, they're parallel. And doesn't that remind you, when the dot product is 0, they're perpendicular? Right? So I like to think of this property here as being sort of complementary, sort of, it pairs very nicely with the old fact about dot products and perpendicularity. Okay. And then lastly, at least lastly for today, because we're about to run out of time, this list is, sometimes it's dependent. Okay, fine, annoying. But other than annoying cases, this list is always in right-hand order. There are the annoying cases we have to say never in left-hand order, right? But other than annoying cases, this list is always in right-hand order. Take any two vectors, cross them, put the cross product last, right-hand order. Very cool fact. And again, you got to worry about the annoying cases, but really easy little proof. Okay, we're out of time. We will draw the line right here. We'll pick up here on Wednesday. Y'all have a good extended weekend. See you later. Pleasure.